Hey everyone, this chapter we'll be talking about shearing stresses in beams. Like the previous chapter where we talked about direct stress in beams due to bending, this builds on that and talks about a different type of force, shearing stresses. So the objectives of this chapter are to define the magnitude and calculate shearing stresses in beams using a formula. Within this formula there's another thing we need to solve. It's called the first moment of the area, so we'll define what that is and how to calculate it. And just like last chapter, we'll define where the maximum shearing stress occurs in the beam. And then we'll also be able to specify a suitable design shearing stress to ensure that these types of shapes don't fail when they are in a service. And then there's this last thing, it's kind of cool, called shear flow. So just like water flows through a pipe or whatever, shear will flow through a section, and we'll define what that is. Now, with this type of bending situations, there are some practical design situations where shearing stresses are important. In particular, there's types of beams used in homes called wooden beams. And these wooden beams are normally not one solid piece of wood. They are laminated smaller pieces of wood together. And they're typically glued with some sort of adhesive. Sometimes they're bolted, but more commonly they're glued. And because shearing stress is a cutting type of motion, the cutting type of motion can cut right through where two of these sections meet, where they're laminated, and cause failure in the beams. Next is a thin web beam. Think of the I-shaped beams that we've solved before in this class. The vertical component in between the two horizontal, that's known as the web. That web, if it's too thin, can also be sheared due to a bending in these particular cases. Next are beams that are shorter with a smaller length. Any sort of cantilever beam or simply supported beam that is relatively short can have excessive failure due to shearing stresses merely because it's short. And these last two are sort of related to the top one where I discussed of wooden beams. If you fasten anything together into multiple sections, where it's fastened together can be sheared when it's bent. And stress skin structures, so this could be anything that has like a brick laminate, it could be any sort of epoxy laminate, some topping for concrete. When it's bent, at that intersection where it's touching the other section, can be sheared due to these shearing stresses. And so we need to define that and figure out what the maximum shearing stress is. Okay, so here's the formula that we'll need to calculate all of this. Now it's tau, just like tau was used for shear in the first or second chapter of this class. But now it's defined for shearing stresses. It's equal to capital V times capital Q divided by IT. Some of these values look familiar to you, but some are new. V is the vertical shearing force at the section of interest. Now this might be given in the problem statement, or like the last problem where we needed the maximum moment from the shear and moment diagram. This V comes from the maximum shear from the shear and moment diagram. So you may be given a problem with some loading conditions, and you'll have to draw and calculate the shear and moment diagram. And then you will take the maximum shear to determine the maximum shear stress due to bending. And just like last time, this is an absolute value, so if you have a negative value that's higher than the positive value, you need to choose that because that is the maximum shear that is overall happening, whether it's negative or positive. Then I is the moment of inertia, just like last time. Maybe if it's a rectangle, base height cubed over 12, and if it's any other section, we just use those simple formulas from the previous chapters. T is simple enough. It's the thickness of the cross section, but pay particular interest that it is where you are trying to solve the shear stress at. So the thickness can change at any spot of a section. So it's where you're trying to solve this at. Q is the second objective of this chapter, which is another thing needed to finish this calculation. It's called the statical moment, and it's about the specific section. It's also known as the first moment of area. It doesn't matter too much whether you memorize these names, but it's most important to know this, that Q is essentially half of the area multiplied by y bar. Now, it's not necessarily the same y bar we calculated before of the overall shape, but it is of a specific part of the section. And it's effectively half of the section. So this will make sense when we go over and do an Example. First, let me give you the formula for Q. Q is equal to AP times Y bar, where AP is the area above or below the plane where the shearing stress is to be found. So if you're trying to find the shear stress in the middle, it's just the area below that. If it's a perfect rectangle, then it could be above or below, and that's going to be the same distance. If you're trying to find the shear stress that's 3/4 from the top, then it's the bottom half of that. So if you're looking at any sort of shape, you're figuring out